All right, I think it's a very good time to start. So let me just give you guys a little bit of the introduction about our speaker. So today I'm very honored to have Dr. Yuan Liu to join us today. So Dr. Yuan Liu is an assistant professor at North Carolina State University with joint appointment in the Department of Electrical and Computer Engineering and the Department of Computer Science. Prior to joining NC State, he was a postdoctoral researcher from Massachusetts Institute of Technology. He received his Bachelor of Science in Physics from Tsinghua University and his Master of Science in Electrical Engineering and PhD in Chemical Physics from Brown University when he was a presidential fellow. His research lies at the intersection of quantum information science, theoretical chemistry and physics, and quantum engineering. He's a recipient of the Goodnight Early Career Innovator Award and the ECE Rising Star Award. So, yeah, Dr. Liu, you can start your presentation, and we are looking forward to that.
Great. Let me share screen. Can you see my screen well?
Yeah, we can say that.
Awesome. Thank you, Yuchi, for the invitation and then the kind introduction. It's really happy to be here to tell you a little bit about some of our recent work thinking about how quantum computing can be performed not only with qubits, but also with quantum oscillators. So this talk, I will try to argue that answer this key question of why oscillators can be useful for quantum computing. I will draw connections to leading quantum hardwares, but with a focus on controls and the quantum algorithms that you can run on this hybrid oscillator and qubit quantum processors. And I will highlight some of the utilities and applications, especially on quantum simulation that this new quantum processor opens. So to appreciate this question, this unconventional question, it's useful to broaden the scope of a little bit, thinking quantum computation more generally as a process that happens on some space degrees of freedom over time. If you have that broader perspective, you can roughly sort of characterize, all of this different process in terms of whether space is continuous or discrete versus time is continuous or discrete. So let's keep space continuous, and then let's also keep time continuous. This is basically quantum mechanics of everything. And you can interpret that as just a physics process, or you can interpret that as a computation that nature is doing. But there really isn't that much of a theory behind if you keep everything continuous. And we also know that fully continuous degrees of freedom is really hard to control. So computer scientists has tried to break down all of this into the most simple two-level systems, give rise to qubits.
Right.
But if you keep the time continuous, but the qubit discrete. Now this sort of enters the realm of analog computing, where you can actually talk about continuous drive in pulse. This has improved the controllability compared to the fully continuous time case and continuous space. But also the Hilbert space is sort of limited because one qubit only have two levels. And there's also no bosonic statistics carried. And if you actually keep even discretizing time, now you enter the land of standard sort of circuit model of quantum computation, um, where this scenario is much easy to control than the continuous time case. But also, you can also think about fault tolerance because now every time step, there is only a limited sort of step in time. You can count number of faulty pathways and all that. So give the theory fault tolerance. And after you sort of you work through all of that, you can drive back to keep time discrete, but then space continuous. And then you can have much more interesting bosonic hardware characteristics on your quantum computer. And then there is this sort of new space degrees of freedom will be very hardware efficient. And then the challenge is that there are this analog of magic on CV systems where it's called non-Gaussian resources are really hard to realize and hard to control. And so the talk of today is that I'm going to focus on this upper right quadrature. I will keep time discrete, but I will try to hybridize the continuous space and discrete space all together. And I'll show you that how this hybridized space degrees of freedom can actually overcome some of the control issues on fully only continuous variable systems, but also gets you a lot of interesting utilities and applications. And of course, this whole idea, right, of using continuous variable is not new. Even back then, last century, 1998, there was the first paper that talks about how you can actually do error correction on fully continuous variable systems. And roughly at the same time, Lloyd and Broston was able to show that the first prove how universal continuous variable quantum computation is ever possible with elementary, interactions and optics, and then how you can program systematically arbitrary operators on continuous variable systems. Now, once we have those foundations, then people quickly start to work out all the generalizations of algorithms, including Grover's and Shor's algorithm to continuous variable domain. And all this works out really nicely theoretically. This is roughly 2 decades ago. And then it sort of died down. The key reasons is that I think we might have, do we have any questions on Zoom?
Oh, we did.
Rich, can you please mute your mic?
Oh, sorry. So if no questions, I can continue. The key reason back then is there's really no CV hardware. The only thing you can probably think is really the optics. But then that's fully CV, and it's really hard to control the nonlinear elements in optics to kind of do scalable CV computation. And luckily, fast forward 2 decades and to today, in the past 2 decades, there has been significant progress on thinking about programming, especially on the hardware side, how the CV degree of freedom can be engineered and produced in a scalable fashion, how the fidelity of the CV mode can be sort of increased systematically. So this figure shows you sort of three leading architectures. Nowadays, we make quantum computers. The left-hand side one, this is the superconducting transmon, which is given by the purple circle two-level system qubits, coupled to a microwave cavity, where
Christopher Poon, your mic is unmuted. Can you please can you
Yeah,
please mute your mic?
yeah, I will just mute everyone.
cool. Although I like that sound. Um, So, this green cavity, this is the microwave cavity, sort of a centimeter size, where you can trap microwave photons inside. And the fidelity of this cavity is really good, and the lifetime oftentimes can reach the order of milliseconds. And so you can sort of fabricate and scale this up and make a quantum chip that has both the qubits and the oscillators on superconducting platform. And all these lines sort of connecting different cavities means there are entangling operations between them. But the qubit only sort of couples locally to each one of their sort of cavity mode. And the similar story happens on trapped ions, where the ions actually have qubits or qubit encoded on their spin or hyperfine splitting or electronics degrees of freedom. But the ions motional degrees of freedom actually carries these bosonic modes or quantized oscillators. And then they also couple together by laser. So you can kind of also view trapped ion as a hybrid CVDV quantum processor. And neutral atoms is the same case, where each atom is actually trapped inside a laser sort of optical tweezer. And then the atom is moving slightly. That motion is actually also quantized, and that's the CV. And then the neutral atom's internal degree of freedom are the qubits, the dV. And again, you can sort of have this hybrid CV-dV on pretty much every leading platforms. And the hardware has advanced so much. So now this opens an entire opportunity of rethinking how quantum computation can be performed on these hybrid systems. And of course, from a computer science perspective, every time we talk about, a new computer, right? We wanted to think about this stack, quantum computing stack, where hierarchically there are different layers of interesting problems across the whole realm of computation one can think. Once you have these different devices, now you wanted to ask, on this new processor, what is the universal gate set that actually program this? And if you go a little bit higher, you wanted to even make a compiler that synthesize and translate different programming languages on this CVDV processors. And can you actually also invent new programming language that sort of helps you to program this easily? And what about algorithms and applications? Ultimately, we wanted to ask what value, utility does this new processor really delivers? And today I'm sort of going to focus mostly on the algorithms and applications. But before I do that, there is some sort of fundamentals of continuous variable systems I do want to go through quickly in case some of you don't have, too much of background on this. And in terms of applications, in terms of algorithms, I will sort of talk about three different known fault-tolerant algorithms on qubit architecture, and then show you how this can be generalized to CVDV architecture. And in terms of applications, I'll focus on two primitives. One of them is the state transfer. How do you convert quantum information coherently, deterministically, back and forth between qubits and oscillators? And the second application is on quantum simulation of mixed Fermi-boson matters. So let's kind of go into a little bit about the fundamentals of all of this weird CV states. You know, from a linear algebra perspective, it's kind of very easy to understand. So for qubits, you have two levels. And for quantum oscillators, you can think of that as a particle trapped in a harmonic potential, where the Hamiltonian is given by this frequency, which is a constant, times the number operator n. And the eigenstate of this Hamiltonian defines the energy or how many photons are there in a single mode. For example, this will be labeled by cat 0, 1, 2, 3. And on the right-hand side, this is the energy level 0, 1, 2, 3, representing different energies and different number of photons got trapped inside this bosonic mode. And just as qubit, where you can have superposition of 0 and 1, in oscillators, you can have superpositions of all the possible eigenstate, like 0, 1, 2, 3, or all the way up to some super high integer numbers. And that's the state of a single oscillator. And in terms of representations, you can write this using energy eigenstate, which is also called a Fogg basis. But sometimes it's kind of more intuitive, physically meaningful to look at the same state under a continuous positional momentum representation. And we will denote this cat or bra x as the eigenbasis of the position operator x here. And similarly, you can have the momentum eigenstate, which is defined as the cat p, the momentum, the eigenstate of the momentum operator. And then they are related to this correlation annihilation operator A and A dagger by the simple linear transformation. And by the way, A and A dagger, these are like your qubit sigma plus and the sigma minus. So if you apply A to the state, it sort of removes one photon, sort of de-excite your system by one quantum. If you apply A dagger to the system, it's going to create one photon to the bosonic mode. And in this fashion, under the continuous basis, you can look at the sort of shape of the wave function on the position. And the simplest one are those really just like Gaussians. And a third representation where you can equivalently write down this sort of state in the phase space, which is a two-dimensional space sort of spanned by position and momentum of your oscillator. And then you draw, oh, what's the probability distribution where this oscillator is right now, in which position roughly, and in which momentum. And it's blurred because we're talking about quantum mechanical uncertainty principle. So it's not a dot, but some sort of Gaussian distribution or some other shape. And there are different kind of states you can talk in CV. The simplest one is the vacuum state, which is the zero photon states, which is really just a Gaussian centered around zero. And in phase space, it's a sort of blob on the origin. You can also displace, so drag this state across, in different space. It's like your pendulum, right? You shift your pendulum in different place, and then that's going to give you a different Gaussian, sort of centered around different position. You can also kick the pendulum, although it's in the same place, but the momentum, the velocity of it got changed. That's why if you kick this pendulum from alpha r, and then it's going to increase its momentum. So then you can actually see a different sort of CV states in a phase space. And that's the simplest one. But you can also try to kind of change the shape of the CV state. For example, you can squeeze it. And then the squeezing operator is given by this sort of quadratic unitary in A and A dagger that changes the width of the Gaussian. And that's just like a trade-off in terms of uncertainty principle fluctuations. So beyond the states, so we have to talk about operators because that's the gate that we're going to need to use to manipulate the CV states. Quantum mechanics says that every unitary, right, gates has to be written by some e to some Hermitian like operator h. And in oscillators, we have x and p. So any unitary can be written as a Hermitian of x and p to some nth polynomial degree or some really weird functions of Hn, which is a function of x and p. And you can simplify that function. For example, the simplest one is a linear order polynomial x and p, h1. And then this is some operator that's called displacement. It turns out that just shifts your states around, as we discussed. And then this displacement operator, just like your polys, satisfies some commutational relationship that's a more general version of poly. Poly, if you swap x and y, right, you kick up a minus sign. That's because the phase is pi. But this displacement, if you swap the order of two displacement, they actually kick out a different arbitrary phase where this phase is not pi, but proportional to the product of this displacement amount, that you actually the gate sort of represents. This has sort of deeper kind of physics reasons in phase space from Berry curvature. But simply like from a linear algebra or computational perspective, you can think of this just as like a more general version of the phase that they satisfy different commutation relationships. So there is like an easy way you can make analogy between CV and polys and so CV and DV. So if you think about DV, right, we know Clifford gates are easy, classically simulatable, where Clifford gate C is defined as any unitary that actually conjugate a poly and then returns another poly. And then you can ask the same question, what is some sort of operator in CV that conjugate the analog of poly, which is displacement, and then return you another displacement? It turns out that's going to be the quadratic, order unitaries generated by squares of x and p. So, I'm going to skip all of this, but some representative sort of Clifford operation in CVs like rotation, which means you're going to rotate the phase space of your CV states, or squeezing, which is like changing the shape, right? We see it. And then the other direction of squeezing on different directions. So there is like a very interesting analogy here. This analogy can be drawn not only at a single qubit, single oscillator level. You can also kind of go even to two oscillators. For example, this is a two qubit, so Clifford circuit that generate a Baire pair. Right? We all know, this is like useful for quantum communication. If you actually replace these two qubits into two oscillators, you initialize them in vacuum state. And then you apply this sort of Clifford analogy, like U2, right? You can actually generate entangled state between all the possible photon numbers, like, the eigenstate, the energy eigenstates. And this is like a very highly entangled state. as compared to qubits. Again, the circuit is written down by simply making analogy from dV to CV. And if you wanted to produce the entanglement sort of in different bases, for example, position bases, you just have to change this U2 a little bit, like into some other quadratic powers at X and P. So the idea, the lesson here is that, once you kind of think about the commutation of CV at a very loose level, you can make analogy to dV. So anything you know in dV quantum computing can actually be sort of generalized to CV. And obviously the rest of the talk I'm going to talk a lot about generalizations. But the key to sort of motivate that generalization is to note the similarities in terms of all of this, which operator plays which role, in the whole hierarchy of the computation paradigms on dV versus CV. By the way, if you have questions, feel free to interrupt. And then beyond Clifford, there are magic states. So the analog of magic for CV is actually something called non-Gaussian operators. And, these operators are generated by Hermitian sort of Hamiltonians. That's cubic power in X and P, or higher power, right? Just by, simple analogy. So with that, I think we are sort of ready to talk about some universal gate set that will allow us to do arbitrary computations on hybrid CVDV processors. And if you think about this, well, it doesn't seem to be obvious why a limited number of gate could ever give you universal control on this infinite dimensional CV Hilbert space. But it turns out that you just need three different type of gates. You can then program arbitrary number of oscillators and arbitrary number of qubits simultaneously. And so one of the universal gate set is called the so-called phase-space instruction set. It composed of three gates. The first gate is the conditional displacement given by this definition. This is a unitary, obviously, and it's sort of conditioned on the qubit poly Z, but then says that, well, it's going to displace, because this is a linear in A and A dagger, the oscillator by amount of alpha, right? Sort of entangling operation between qubit and single qubit and single oscillator. And once you have this, now on top of that, add arbitrary single qubit rotations, like the T-gate, Hadamard, whatever continuous XYZ rotation. And then you need a little bit of entanglement between the oscillators. For example, beam splitter operation. So this is the analog of C0 gate between two qubits. You can think of a beam splitter like, a C0 gate, between like two oscillators. And then only the three different gates you can actually, do arbitrary universal control. And this is pretty cool. And you can check this experimental paper where they were able to show this really works on superconducting circuit QED platform on real hardware. And then there is an equivalent different gate set. That's the so-called Fox space instruction set. The key difference is the first two gates, where you replace the control displacement into this different entangling operation between qubit and Q mode. So what is this? It looks weird, but it's really saying, depending on which photon number M Fox states your Q mode is, this operation is going to perform a different Rx rotation on your qubits along different rotation angles, theta m. Note that this rotation angle will depend on m. Right? So again, it's like a highly entangled operation. Once you have that, and you just add a little bit of uncontrolled displacement, meaning that just drag the oscillator along in arbitrary sort of way. And then plus beam splitters. Again, the three different gates are universal. You can program any arbitrary computation just by tuning all of this theta m, and then the displacement amount and the beam splitter sort of phase shift and rotation angles. And the second gate set is more useful on circuit QED, superconducting platform, while the first gate set applies to both trapped ions and the circuit QED relatively easily. So that's about the basics. Um, so now you have the universal gate, and then you know the foundations. Now you can think about how you can actually synthesize all of the gates together using some algorithms, right? But we also know that we have the CV Grubers, we have the CV Shor's algorithm, and then we have the CV Deutsch-Josser. This is also 2 decades ago. But like those are really special algorithms. And in the past decade, there has been lots of interesting advancement in DV algorithms that's really, opens the whole plethora of zoo of algorithms that allow you to pretty much do anything on DV quantum computers. So the interesting question to ask is that can we actually develop, similar algorithm, very flexible, powerful algorithm primitives on the CVDV processors beyond, the Shors, Groovers, all that stuff, to allow us to actually program or synthesize or realize any possible computations in a slightly more flexible fashion. And if you look at the landscape of DV algorithms, quickly, you will find something called the trotter or product formula enters, that actually is a really nice algorithm to perform a Hamiltonian simulation, simulating quantum dynamics of any systems. And there's also linear combination of unitaries that sum up different unitaries. And more recently, there is also this algorithm called quantum signal processing that performs polynomial transformations on some block-encoded operators that performs arbitrary, computations. So it would be nice to see that how all of this could actually be generalized to CVDV. And indeed, it turns out it's all possible. And in the rest of, I guess 10, 15 minutes, I'm going to try to spend a little bit of time focusing on this quantum signal processing and tell you how a CVDV signal processing algorithm can actually be invented and how useful it will be to many different applications. And I'll mention a little bit about also a linear combination of unitaries and product formulas on CVDV processors. But before I move on, any questions about whatever I talked about fundamentals?
I think we are good. Yeah.
Okay, awesome. So let's look at quantum signal processing. I wanted to talk a little bit about history here, because QSP is not actually from nowhere. It's from a very common experimental sort of technique called the nuclear magnetic resonance, where you drive magnetic field to control spins, right? So in early days of quantum computing, around 2000 again, the most well-controlled qubit is actually the nuclei spin. And the only way you can control those is by driving AC and DC magnetic field. But it turns out that the gate you actually do, the gate parameters can be tuned by the magnetic field intensity and phase. But the field sometimes has bias, has drifts, and then your instrument, has some unknown, uncalibrated errors. As a result, most of the errors, there's one dominant error called coherent over rotations, which says that if you wanted to do this rotation by angle theta along some axis phi, let's say you wanted to do like pi over 2, but it turns out that the device actually do is pi over 2 multiply by some small constant, which is bigger than 1. And this small constant is, kind of epsilon hidden unknown for device, but it's actually roughly unchanged over time, right? So the key question now here is that people are asking, well, if I can ever only do imprecise rotation, can I actually concatenate many of these imprecise pulses, single qubit gate, to produce a much improved, accurate single qubit rotation by pi over 2. So that was the question in the early days in MR quantum computing. And this give rise to a whole sequence of sort of work named after composite pulses. It turns out that if you actually do this 4 pulses, where every theta is actually imperfect, over-rotated, but if you carefully tune your rotation axis, phi1, phi2 here, given by these numbers, you can actually show that this 4-pulse sequence actually realize the almost perfect pi over 2 rotation, where the error is suppressed from epsilon epsilon score in expectation values to actually epsilon to the 6th power. So basically a cubic suppression in errors if you actually use 4 pulse. Right? So this is to some extent the counterintuitive. You think that you have more, error things. How come you can actually have a better thing? But the key is that here the error is actually constant. You can actually cancel the error by carefully tuning, the rotation axis. And this already give you a notion, this cubic scaling, right? It's sort of manipulating the errors according to some nonlinear transform that the errors now is suppressed. Now, this whole pulse engineering idea, sort of matured a little bit over the span of 1 decade. It turns into a much more powerful and general algorithm called quantum signal processing. So the idea is that, well, let's not think about this whole thing just as a pulse engineering where the epsilon is some given unknown errors. Let me just say I'm actually given arbitrary single qubit rotation, WA here, where A is unknown, and it could be anything. And this is Rx rotation, by the way. And I can also try to find a orthogonal rotation, let's say the Z rotation. And the whole theorem says that if you concatenate this unknown Rx rotation WA with this known RZ rotation, tunable, and if you do this D times, the result of this 2x2 unitary on a single qubit, where the upper left block actually turns from A to a polynomial of PA, where the degree of the polynomial is precisely D. And also, this polynomial can satisfy some conditions in a sense that, well, if the degree of sort of PA is roughly sort of less or equal to D, then the degree of Q is roughly less or equal to D minus 1. And this polynomial also have to have parities in a sense that if D is even, PA could only be an even polynomial. And if D is odd, PA could be an odd function. And then they have to satisfy some unitarity conditions just by, because the whole thing has to be unitary. And, this is a very sort of abstract, high-level mathematical statement, but it's also nice because the backward direction is true, which says if you have any arbitrary degree D polynomial that satisfy these 3 conditions, there exists a set of D phase angles, D plus 1, sorry, phi 0 through phi D, where you can chain just the whole circuit together, write down the circuit in that way. You will realize that polynomial. The reverse direction is especially powerful because that's really how any computation could ever be performed. If you think about Gruber's search, it's actually just making that polynomial a linear function with a slope bigger than 1, because that will allow you to actually amplify a small number, into a bigger number in the y-axis, right? And if you think about Hamiltonian simulation, it's really e to the I hx. And then if h is your a, right, then you just have to find a polynomial that's roughly e to the I x times t. And then you're done. So in that sense, this is a very flexible sort of polynomials. There's one question from Ali asking, are the polynomial members of a special polynomial family? It depends on what's the phase angle. If you keep all the phase angles 0, you can show that this PA is actually the Chebyshev polynomial of TK. Um, and if you actually, change the phase angles to different special values, you can show sometimes it becomes Bessel function, sometimes it become other functions. And in the most general sense, it's actually a linear combination of the Chebyshev polynomial. But the most general constraint is you really just the only mild constraint given by this. Hope that answers your question. Cool. All right, so let's move forward. So, once you have this general theorem, you can really just look at this composite pulse, BB190 pulse, as a degree 9 QSP, where all the phase angles are actually given by, phi 1, phi 2, and sometimes 0, actually. And this is the first version of quantum signal processing algorithm. And after that, there has been many, many generalizations. For example, this is on the single qubit cases. And what if you actually change this small a into a matrix or Hamiltonians or bigger operators? And this gives rise to the whole theorem of quantum singular value transform theorem, which allow you to manipulate a higher dimensional subspace using a polynomial transformation. And then there's also the generalized version of QSP by Nathan Weeb and Daniel Mottola, where they say, oh, this parity constraint can be relieved just by simply changing this z rotation into arbitrary xyz rotation. And then your polynomial will be very general. And you can also say, well, this is a px, a single argument polynomial. What if I wanted to realize, pxy, where you have two variables? And this gives rise to a family of algorithm called multivariate quantum signal processing algorithm. And more recently, you can say, oh, well, this, single qubit is SU2 dynamics. Can you actually realize, an array of, n polynomials in the SUN bigger matrix? And indeed, that's actually possible. So this gives you this SUN generalization of QSP. And there's also SU11, all that, interesting results found by, and also connections to nonlinear Fourier analysis found by applied mathematicians. And also this phase angle finding algorithm has been very mature in the sense that if you know the polynomial, there is very efficient classical algorithms that can generate all of this phi k. So, this really makes this algorithm very powerful and flexible. And so that's the basics of quantum signal processing. And obviously, we don't really care about DV in our talk today. What we really care about is CV. And the simple question here is that can we actually do this nonlinear transformation to use that as a tool to control quantum oscillators? If you think about a general sort of a unitary operation on a single qubit coupled to a single oscillator, it got to be just like tensor product, right, between the sigmas and some functions of x and p. And if there is a way I can approximate this arbitrary nonlinear functions of x and p using QSP, then I can probably, do this. That would be really good because then, mission accomplished. The intuition here is that this BB190 pulse sort of does this nonlinear transformation on the noisy classical variable, which is the error rotation angles. And in the quantum oscillator case, the classical variable theta now becomes a quantum operator x and p. So the question is, does the whole machinery still works if you transform x and p into a quantum operator, where the quantum operator actually should have variance, right? So that variance, you can roughly look at that as the sort of errors in your classical variable. If you're kind of thinking that way, intuitively, this has to work. And indeed, the answer is true. So I will give you a more sort of linear algebra concrete viewpoint of this from a language blocking coding. Let's look at this single control displacement operation I introduced before. So this is again the simplest linear entangling unitary between a single qubit and a single oscillator. And if you write this out, you can show this is really just a diagonal matrix on the 2 by 2 of the qubit, where the matrix element actually lives in the oscillator's Hilbert space, which is a simple displacement operator. And immediately you realize the simple entangling operator is really a block encoding of the displacement operator, right? So it's sort of like a block encoding of the oscillator inside the qubit. And you can sort of just treat this as your W operator I showed in a single qubit QSP. Another way of looking at the same operator is to kind of combine this K and X together, and then call that a abstract rotation angle theta. And then the same operator now becomes a single qubit rotation, but then the rotation angle has some variance, or whatever distribution governed by the oscillator wave function spread, X, right? So then this is really close to the classical picture, where the error now on the theta is introduced by not the over rotation epsilon, but by the spread wave function of the oscillator. And from that, obviously things work, right? So I'm going to skip all of these examples on CAD state preparation using this. But let me just give you a formal machinery statement about this. So given this block encodings, where you could block encode either X or P of your oscillator operator, you repeatedly apply this block encoding WZ and a single qubit rotation along the sort of X direction. By tuning this rotation angle phi j, you can realize the final operation is a block encoding of some nonlinear operators, F omega, where omega is really this displacement operator in X. And where this sort of F omega is a Laurent polynomial of omega, or I should say W, because I'm really using W. And the coefficient Fn is tunable by all of this, rotation angles on the qubit. So in the end, what you're realizing is some weird functions Fx on your oscillator. And if you use P, the second, block encoding, you can realize some Fp on your oscillator. And this is really nice. But you can also kind of make this more general, where you say, I'm going to actually iteratively use both block encoding of both X and P, and interspersed by single qubit rotation. And this will actually give you a block encoding of two varied polynomial. And then the result of this is actually going to be a Laurent polynomial of both X and P quadrature. And this is a more flexible or more generic way of performing nonlinear operator synthesis transformations on the continuous variable oscillator's phase space. And again, you can tune all of these qubit rotation angles, to get whatever sort of functions you want. And obviously, all of this admits some generalizations again, in a similar spirit as one did on the qubit case. And one thing I wanted to point out is that if you're staring at this sort of operator a little bit, you realize whatever this thing did on the oscillator, this fx, is actually a periodic function, where the period is given by 2 pi over kappa, where kappa is the small sort of displacement you had on the W operator for your entangling control displacement. So in a sense that the sequence is turning the infinite dimensional phase space, kind of making that periodic. And then you synthesize the operator into each unit cell, each periodic cell in arbitrary fashion. But you really don't have the power to actually manipulate the entire phase space, because that's infinite. You're going to need like infinite long phase sequence. But this is oftentimes sufficient, because mostly any initial state, physical initial state you care about for computation on the oscillator has to lie within some regions. And if you make your periodic, unit cells large enough to capture that region, whatever you care about, then it will be good. And so that's the theory of quantum signal processing's sort of background noise. So I think I'll have to skip all of this LCU constructions, but the whole point is that, LCU can be generalized to CV domain as well, where instead of realizing a sum of two unitaries, you can actually use this oscillator to realize a continuous integration of some DV unitaries. And this will get by the discretization errors oftentimes you have when you artificially wanted to truncate the integral into sort of continuous sum. And this has some nice applications to a recent algorithm on linear combination of Hamiltonian simulations, because oftentimes people do it by discretizing that integral. But you can actually do this continuously using CV oscillator, where you can get away this discretization error easily, and it's more natural to solve partial differential equations. And obviously, product formula is doable as well. So I'm going to skip all of this. And so what I sort of focused, talk about is mainly this: how do you control a single qubit and oscillator in arbitrary fashion? And then we see that many things can be generalized indeed from the DV algorithm land to the hybrid CV-DV land. And there is this part that I didn't talk about in terms of how do you actually synthesize a multi-weight qubit and oscillator entangling operation. And for example, if you wanted to do two qubit entangling gate, you can actually mediate that using oscillators. And all the trick is the Berry phase that I talked about from the commutation relationship. And this is actually the Momo-Sorensen, the mechanism of how you realize Momo-Sorensen gate on trapped ions, which is mediated the qubit entangling with motional modes. So with that, so we can actually kind of put everything together. And now we have pretty much the full stack, figured out the foundations of the computing with this oscillators and qubit platforms. We can now sort of put the whole chain together. Let's say we are given some applications and we have some parameter size. We can actually map those to this hybrid processors, and then we do our compilers. And then we will be able to translate all of those computations into gate set in the instructions gate set. And we'll be able to count the resource requirement. And that will give us some good estimation in terms of how powerful this processes will be as compared to sort of qubit platforms. And to support that statement, there has been lots of different works done by sort of our collaborators. So for example, this one is a Hamiltonian simulation compiler that automate the synthesis of arbitrary CVDV Hamiltonian simulation. And this is useful for example, Fermi-Hubbard model or any spin-Boson coupling or Fermi-Boson coupling dynamic simulation. And so this is the link to the paper and the GitHub repo where you can check out. With that, so let me actually kind of pause here a little bit just to see if you guys have any quick questions I can clarify before I talk about applications.
Are there any questions for our speakers? I think we're good. Yeah, we can.
Okay, all right. So for the interest of time, I'm probably gonna have to skip some of this. But the first application I'm going to talk about is actually relevant to how you convert state. For example, you're given n qubit state. And are there any unitary operations protocols you can figure out that apply this to a joint qubit and the vacuum oscillator state, and then returns the qubit to the all zero state, but it stores all the information on the qubits into the bosonic mode, the oscillators. And this is the so-called state transfer problem. Or from a sort of more engineering signal processing perspective, you can call this a analog to digital conversion or digital to analog conversion protocol, where digital really means DV quantum computer and analog really means CV quantum processors. And this is also useful for quantum networks and sort of distributed quantum computing, where you wanted to shuffle, the computed states across the network, because the network is oftentimes transmitted by photons, which are bosonic modes. And the challenge here is that, we really wanted to do this fully coherently. Know that I just apply unitary. I actually never do any computation. I don't want to do post-selection. And I wanted to have this systematically improvable accuracy so that, things are pretty much accurate. And also this unitary has to work with arbitrary state of qubit, regardless of what's the sort of CX, the coefficients, right? So from the sort of outset, it's not that easy to do. But it turns out that there is a way that you can achieve this by using quantum signal processing that we mentioned just now. The idea is this. Let's say you have your qubit, n qubit, and one oscillator. You can first try to entangle each qubit computational basis with a different sort of coherent state or a sharp Gaussian peak, wave functions in a CV oscillators. And so this is the first stage. And this entanglement can be done by simply doing a whole bunch of, control displacement by different displacement amount, n of those, actually very cheap. And once you do that, the information is sort of already inside the CV, but it's entangled with DV. And now you have to disentangle all the DV qubits from the CV. And the way you do that is to selectively flip each one of the qubit by a Pauli X conditioned on the nth bit representation of the CV position that acts that floating point number. And you can show that if you can do that, you can actually completely disentangle. And the idea is, how do you actually then, perform this disentangle, selecting the bit? One simple way you could do this is to actually synthesize a square wave as an operator that applies to your CV, and then conditioned on each one of the DV qubits. For example, the first gate here really says that it's going to condition on the most significant bit of the position X of the oscillator, and then flip this most significant qubit, because that bit on X is actually labeled by this first qubit. And then the MSB -1 is actually labeled by the second qubit. So you can synthesize this second periodic wave that disentangle the second qubit. And then, you can keep doing this across all n qubits. And in the end, you can show that, this simple protocol really achieves some really improvable fidelity, almost close to unity, as a function of the spacing between the displacement you do, and also the width of your Gaussian squeezing sort of CV state. And also this epsilon is the QSP synthesis approximation error to your ideal square wave. And then of course, n is number of qubits. And you can actually systematically suppress this fidelity to 1 by just reducing epsilon and this ratio between delta and sigma. And then the gate complexity is kind of high because the second step here, every one of these has to use lots of gates. And then the time complexity is also high. But this is actually cool because it really achieves something. So I will skip this and then just to kind of show you a better version of this. So this is numerical demonstration that we did to transfer like 3 qubits into oscillators, and then to see what's the sort of purities and all that, right? And what you might ask, right? What can you do with this? You transfer this DV to CV, and one of the things that we learned from even classical computing is that different computing hardware has different characteristics, where some tasks can be really easy on those. For example, you wanted to ask what's simple on oscillators, and it turns out that quantum Fourier transform, as we oftentimes do, and very useful for qubits, is actually pretty easy on oscillators. The reason is because if you really just look at the position operator X, and then you transform that using the free evolution of your oscillator Hamiltonian, that can turn into P. operator, momentum. And you know X and P form a Fourier conjugation pair. And therefore, Fourier transform on oscillators is really just one gate instead of n squared gate on n qubits. So if you can encode all of this qubit information to the positions of your X, waiting for one gate, you're done. It's so easy. And then, oh, how do you encode that? We already did that because we know how you can transfer n qubits into positions of X, right? So you're basically done. And so then this gives you a really simple quantum Fourier transform circuits on jointly CV-DV platforms. But the goal is to perform a QFT on the initial n qubit sort of circuits. You perform state transfer from the qubit phi to the CV mode, and then you wait for a quarter period, the single gate Fourier, and then this displacement is a single gate that just shift the phase and all that. Once you are done, you run the state transfer backwards. You can actually transfer the CV state back deterministically into the n qubit again, where you can show that the qubit state now indeed becomes the QFT of the original initial state phi. And you can actually use different, versions of QSP to do roughly similar things, which I will kind of skip. And so this is one of the paper. Right. So what's the caveat? This all looks too good to be true. Of course, the caveat is that the whole protocol need exponential runtime, as I mentioned, because the gate count is 2 to the n. And there's no way you can get around this because the Hilbert space dimension is 2 to the n on qubits. And then you squeeze everything into the phase space of a single oscillator. Therefore, the displacement amount, the volume of the phase space has to be, 2 to the n. But, we were asking, is it actually possible to parallelize this over multiple Q modes so that you can actually reduce this exponential scaling and dramatically? And so my postdoc sort of thought about this, and he come up with a very nice way of performing a parallel multi-Q mode state transfer. The idea is that if you have, a 2-qubit, for example, system, you can actually transfer just a small patch of qubit to one mode, and then you transfer the other patch of qubit to the second mode. And then you can use the tensor product of the mode to actually quickly scale up this dimension, Hilbert space dimension you need. And this works, not only in this 2-qubit case, 2-Q mode case, it actually works for an arbitrary number of n qubits and m Q mode, where you can actually transfer n over m qubits patches every time to a single Q mode. And you can show that, this really works. And the trick is that you have to rewrite the original qubit state instead of a binary representation, but you write that as a D-array representation, where D is roughly equal to 2 to the n over m for each one of the local sort of qubit dimension. So the key of doing this, right, is to come up with some analog of QDIT Fourier transform, like the analog of sort of Hadamard, QDIT Hadamard gate, and QDIT to QDIT entanglement gate. And so we show that this is possible again by some native CV operations and a little bit of shuffling of QSP and all that stuff. So skip all of this, but in the end, what I wanted to show you is that there is this parallel version of sort of QFT that can realize, first of all, state transfer, and then you do a giant CV QDIT QFT, and then you transfer the state back. You can show that compared to the single Q mode complexity exponential, now the multi-Q mode complexity is exponentially reduced. Instead of 2 to the n, you actually have 2 to the n over m, which is actually pretty small. And then with a m multiplicative factor, which is oftentimes small if you control m well. And in terms of fidelity lower bound, you can also kind of show that this fidelity also can achieve unity, but now you have a little bit of overhead. So introduced by this QDIT, CV QFT that you had in the middle. And you might want to ask, right? So all of those are sort of asymptotic scaling. What's really the break-even point? How many CV truncations you wanted to use so that this second way of doing QFT on n qubits is actually, much faster than doing the qubit QFT initially originally. So of course, this depends on the gate time of qubit and oscillators. So we derived, some relationships in terms of break even, showing that if the gate time ratio is bigger between qubit and oscillator is bigger than some relationship given by the accuracies of your QFT and the local qubit dimension on oscillators and um, many other things, you can show that there's a break even. And this figure really shows you numerically where that break even will happen, depending on accuracies and qubit sort of oscillator energy level truncations. And so I think I'm going to wrap up here roughly, and I'll skip the second application, which is on quantum simulation. But the whole idea is that, you can map to some chemistry stuff to this, oscillator CVDV processors. You can do nice things. And one thing we did is photosynthesis, energy transfer in chemistry. And then the other thing we did, is the simulating rotation, vibrational coupled dynamics in scattering experiment in sort of chemical physics. There is like some interesting things that you can map systematically any rotation vibrational Hamiltonian chemical physics into a circuit QED bosonic mode using this theory of algebraic theory of molecules, even including anharmonic vibrations. And so I'm going to skip all of this and then try to conclude. Just to say that, one of the things we're aiming to do an experiment is to modeling this rotational induced molecular dissociation in collaboration with our collaborators at Rutgers University. Okay, so let me wrap up. So I hope my lecture here today is tell you that DV and CV combined together really give you a very powerful new paradigms for quantum computation. And then the physical instruction set has been established, and algorithms and compilers and benchmarkings are all in place to explore lots of interesting applications. And then there are many sort of quantum computing system challenges, of course, for this audience. For example, how can we ever make this even more robust, integrate fault tolerance and logical bosonic mode into the whole paradigm, how error propagates, and can we build even better compilers, explore parallelism, what are some primitives of quantum memories on these architectures that we can think? Are there any even more advantages, especially exploring some unknown territories on communications and distributed quantum computings? And so I'll wrap up here. And thank you for your attention. So this is, our collaborators working on the CVDV front, and we also have many collaborators unlisted here on these slides. And this is a sort of a list of references on some of the relevant papers I talk about today. And I'll stop here and thank you for your attention.
Yeah, thank you, Dr. Liu.